means what in general? Together, share. So like covalent bonds, they share. Cohesion means that the water sticks to water. What does adhesion mean? Somebody else? Jake. Right, so like water can stick to glass. Silicon dioxide is the formula for glass. So water sticks to glass, just like you can see like on the meniscus of a graduate cylinder. It's able to creep up the sides due to adhesion. What else do we read about? Crystal, do you have this one? Is that a hand? Okay, never mind. Abby.
Water access skin to like fingertips.
Right, so the surface tension ability of it. So the skin nature, the top of water, a surface of water has high amounts of surface tension because what is water doing with water? What kind of bonding? Is that a for real bond or a fake bond? That's a fake bond, right? It's just an attraction. We call it a bond to screw people up, like us, right? Because like everything's gone. So this right here is actually a hydrogen bond. And it's actually just the attraction of two water molecules. So it's just cohesive. That's all. That's all surface tension is caused by. All right, so water is pretty easy. We know a lot about it. Anything else you guys read about? Yay, nay? Nay. Abby. Come do ionic. Everybody tell her properties of ionic bond. Everybody?
Metal. That's not a property. Don't write that.
What's it gonna mean?
Property of metal.
All right, somebody ionic bonds. Conductive when though, not all the time.
In liquid state.
Okay, so conductive and then L next to it. What else? So metal and non-metal. We're gonna both use information. Conductive in liquid state, non-metal or metal, non-metal. So just put M and M and M. What else? Shout it out, loud and proud. Strong lattice energy, so strong LE. Means so strongest. We were saying IMF, but it's strongest lattice energy is what do you mean by that? What else? Crystalline, yes. High melting point, right? Because of its lattice energy.
Solid state.
Yes, solid state at room temperature. Thank you.
Yes, solubility. Say that again.
First word, solid state. Solid state. Oh yeah.
Hard and brittle.
What else did we just say? High melting point. Okay. We still on. We'll make a line. All right, and I'm gonna go. Just put it on top of mine. It's good. All right. So what are we gonna say about covalent then?
Molecules.
Okay, I got you. Thanks, darlings. I'll let you write your hurry. So we got molecule. I heard that. MOLE. Apostrophe C. Give me more.
Gas.
Non-metal.
Low melting.
Gas. Low MP. Melting point. Low solubility. What do you mean by solubility, though?
Dissolve in water.
Dissolve. That term is just thrown around willy-nilly.
Energy it takes to break up.
Yeah, we'll talk about that. I'll put low solubility just for kicks and giggles. I like solubility better than dissolve, though. Anything else? Non-what?
Non-electrically conductive.
So non-conductor, non-conductive. So AKA an insulator. There's a better word for that. Insulator. Huh? What kind of IMFs do molecules have? Because so lattice energy, or the lattice structure, is what creates an ionic bond. These have three they can take on. London dispersion, dipole,
Yes.
hydrogen bonding. So really anything can do that kind of stuff, like water can, ammonia can, carbon dioxide. There's all kinds of stuff like that. Metallic. Metals and metals. What else? Delocalized electrons. Yay. Delocalized. If I can spell this. Delocalized electrons. That means what can happen with those electrons? They can do what? They can flow, which is what essentially? No.
What is it?
Electrons flowing though.
Oh.
What is that? Huh? Electricity. You guys can't realize that there's the only thing electricity is an electron moving from point A to point B. That's it. How do you make electrons move? You push them. How do you push them? You have to force electrons behind them to become mobile. It's literally, you've heard of a generator. You've heard of a motor. All this is you have copper wire and you've got a magnet going around it. Well, what's a magnet doing with the electrons? It's making them move. The electrons, the positive end of the electron, the positive end of the magnet's pushing, the negative end of the magnet's pulling or attracting. So it does this thing where it just rotates around, it just pushes the electrons through, all the way through to your house. That's it. Electricity is really fundamentally easy, but it took us a long time to figure that out. Okay, so mobile electrons or delocalized electrons helps with that. How about melting point?
No, way high.
Probably high, because those delocalized electrons can really attract to their neighbors a lot. All right, so what is water, and which of these does water fall under? Right, and we know it's covalent because we know the H and the O bond through a covalent bond. What about, well, do I want to show you this yet? Yeah, I'll show you this. All right, we'll jump back on water in a second. Let's do this first. So of these, you might want to write down the formulas if you can. Of these three, sodium bicarbonate, sucrose, sodium chloride, which is conductive in solution, which dissolves in solution, which ionizes in solution. So maybe write down the formula. Somebody shout out sodium bicarbonate. Na what? HCO3. Sucrose? It's like glucose. Give me glucose. Give me glucose. C, what is it? Yeah, so that's glucose. Sucrose is C22. No. C11, H22, H22O11. That's what sucrose is. Sodium chloride? NaCl. Okay, so knowing that much, which is conductive? Or which are conductive? It can be more than one.
1 and 2.
So one is conductive, and 3. Okay, let's check that in a second. Okay. Dissolves in solution? 3 for sure. Does sucrose dissolve in solution?
No.
I'll give you the common name of sucrose. Anybody know it? Sugar. Table sugar.
Yeah.
All right. Does it dissolve in solution?
Yeah.
Who's made sweet tea? We live in the South, people. Okay. What else? Does baking soda dissolve in water? That's baking soda. Okay. Which one's ionized? Different than dissolve. Sodium chloride. Okay. Anything else? Let's just check, right? All right, so if I were conductive, what would be floating around in water or in solution? I like that word. You're going to say it. Go ahead. Electrolytes? That was on Ring Guide 17? Yeah. Electrolytes are ions in solution that conduct electricity. They allow for electrons to jump, and move. All right, so if I were conductive, I should be able to make ions in solution. So let's double check that 1 and 3 were right. Here's 1, 2, and 3. Will you hit that light for me real fast? And I've got sodium bicarbonate. I've got sucrose, and I've got sodium chloride. Go ahead and do all of them. All right, can you guys see this a little bit? All right, so if I put this in baking soda, the little light should glow if it is going to be conductive. You can see it does, right? All right, so that definitely is conductive because it's conducting electricity. I have a battery connected. The battery, this down here, you need to complete the circuit. There's 2 little prongs. Completing the circuit means having conductivity of the solution. All right. What? Put it in water?
No, you type this shit.
Well, now my hand's not electrolytes, but I can't tell if I'm thinking it's putting electricity through my hand. I can't, like, what's the word? You're thinking placebo effect. I can't tell this. I don't think so. Okay. Now this is DI water, deionized water. Just pure water. Conductive or non-conductive? Why? It's just straight up H2O. There's no ions. Non-conductive. Right? So I can go stand in pure water. I can drop that hair dryer in there, nothing's gonna happen. But if I stand in water that's not deionized, like my tap water, or the ocean, or whatever that may be, whatever, oops, just spilled a bit. This is soluble, just BC dubs. Okay. Oh, I just put my finger on there and there we go. Alright, so now there's nothing on there. I put salt in there, it definitely is conductive. So pure water by itself is not conductive, but once you put ions in it, it is. And then sucrose, conductive or non-conductive, what do we say? We said sucrose number 2 is not, so let's confirm. Nada. I'm sorry. Nada. Okay, so you guys know what the difference is between dissolving, ionizing, and conductivity. Ionizing means ionic compounds break apart. But all these dissolve. Every single one of these are clean, and except it's not having that time to dissolve it away. All of these dissolve in water. So the word dissolve is used wrong all the time. The word dissolve just means water surrounds it. So I can have sucrose, C22H, I did it again, C11H22O11. Here's that big, huge molecule of sucrose, and water just says, hey, we're just going to like surround the perimeter here. And it's literally just surrounding it. That's all dissolve means. Okay? Ionize means actually create those ions in solution like you thought they would. So those two things are used interchangeably a lot, but they're not interchangeable. Conductive means that you've created electrolytes. Well, which one does this match? Ionize, right. Conductive is because it can ionize, not dissolve. Okie dokie? Alright, so those are some terms I wanted to get straight. Alright, I have a video for you. Turn off my little Pandora. And let's watch this video, and then we'll talk about water a bit more. Oh, let me actually make this bigger for you. It's super interesting.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. Why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high heat capacity, and changes in density based on temperature.
Alright, those are things you need to know about water. Give you a picture of that right now. Watch this video again later. I told you I'm doing water in like 15 minutes, 10 minutes. So universal solvent means that it's a very good dissolving agent. It can force things to dissolve or force things to ionize very well. Cohesion, adhesion, we talked about. High surface tension, we talked about. What's causing high surface tension? Hydrogen bonding, right. High heat capacity. That's why water has 4.18 joules per gram degree C, whereas most metals have something like what? 0.1, 0.4. It's so low. Water, you can heat that baby up. It's not going to change temperature until you max out at 4.18 joules per gram degree C. Other metals, you put just a little bit of heat to it and it warms up. So water takes a while to heat up, and it takes a while to cool down. Changes in density, hot water or cold water? Who do you think is more dense?
Cold water.
Cold water, actually. So hot air rises, right? Hot air rises because what? Less dense. So air particles that are hot are way spread out. Less dense. Air particles that are cold are really close together. More dense. Same thing with water, it's just not as drastic.
Let's take a look at each of these in turn. Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces, and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
They don't actually freeze like goldfish do in water. Right, Alex? Okay, so let me go back here. We pretty much just went through everything for water because it's really quite easy. I thought my little clicker would work. Yes. Okay. I feel like we know this stuff. Yes. Molar mass, density, properties. I'm not going over that. IMFs. We know hydrogen bonds, right? We know it causes all this stuff. Low vapor pressure is the only one that you didn't write down earlier. Low vapor pressure means that okay, so vapor pressure, what does that sound like to you? Water vapor doing what?
Evaporating.
Evaporating. What is pressure caused by? The container, right? So if I have low vapor pressure, that means I don't have very many vapors bouncing off the sides of the container walls, right? So girls who, or people who ever have the air polish on, you get some acetone out and it hits you in the face, right? It's very volatile. Or some guy walking around with a lot of cologne, very volatile, right? So that stuff hits you in the face. It vaporizes like that, no problem. So would I have a high vapor pressure or low vapor pressure? High, because it vaporizes very easily. This water, you don't open a bottle of water and go, oh man, I smell of water, right? Because it's not vaporizing very fast, so it's just not causing a lot of vapor. So therefore it's got a low vapor pressure. All right, yay water, polar, geometry.
Linear.
Look at that. It looks bent to me. What's over here? Lone pairs. Thank you. Yes, I got you. Lone pairs, right? Lone pairs. And it's bent because you can see that. What are the lone pairs doing to this bond right here? They're deflecting. They're pushing it away, right? That's why it's called valence shell electron pair repulsion theory. It's repelling that to push it away, which makes it no longer linear, makes it bent. Ooh, ah. Do it with me? Ooh, ah. Okay, that was close enough. Hydrogen bonds in action. They're not actually bonds. Surface tension we talked about, minimizing the amount of surface area with the air. You're trying to pull it together so that you form a drop. Cohesion there. Surfactants we went through. Oh, I didn't talk about the actual definition. surfactant decreases surface tension. That's why water is, okay, the oil spill and the, oh, remember this, yes? They had a big oil slick on top. They used surfactants, things that would break apart the oil and lower the surface tension of the oil so that it would disperse throughout the water. Well, do you think oil dispersed through water is a good thing?
No.
It's not a great thing, but it's better than a fat oil slick on top. Because a fat oil slick on top doesn't allow sunlight to penetrate the water. Well, there's phytoplankton and other organisms that need the sunlight in the water, right? So we'd rather have the oil dispersed throughout the water column than just straight up on top. So surfactant, another name for that, are surfer detergents. We talked about this briefly at the beginning. We can also use chemical surfactants that help with the environmental catastrophes. Yeah.
So, but wouldn't it be easier to clean it up faster
If you can get the, there are these things that are like mops. They can go out there and they can suck up the oil and absorb the oil. However, things that have, if they can't do that fast enough, if the oil spill is too widespread, they disperse it. Dispersant, the oil droplets can get eaten by fish and other water organisms or aquatic organisms. Sometimes that's okay because they can digest it somewhat, but they can't digest those extreme amounts. They can just disperse. So they have to go through the EPA and get these dispersants verified that they're okay for the environment, because actually there's pros and cons to both of those as well. Another thing that they do is they have organisms like bacteria. They're called hydrocarbon eaters. So oil's a hydrocarbon. The bacteria that are naturally living in the water eat the oil, so they can eat a little small droplet of oil better than a big slick. So they're hoping that they can proliferate, yeah, that word, the bacteria cultures prior to dispersing it, because they need the bacteria to eat it. Okay, yay, chapter 16, ready? Question?
they all like stick together but with hot
Water? Yeah, okay.
If you like, geez, like, if you like it's like extended on it, it just kind of like comes down. So if it just barely breaks that, then it just
It should penetrate the water, yeah. That's why things that are more dense, I'm not sure exactly, things that are more dense can penetrate the surface tension because it's denser, so it can actually break the surface tension and take it. Alright, do me a favor, draw something, you got 2 minutes, draw me a picture of solute versus solvent versus solution. I had somebody last year draw me a cute little polar bear proposing to a grizzly bear, and they were going to make a solution, but they didn't mix, because water's polar and the grizzly bear wasn't. Like dissolved slide? We're going over that some more today. So give me something at least that lets me know that you know what a solute, a solvent, and a solution is. Within your notes someplace. If you want to draw a solution and label it, that's fine too. And while you're thinking about your creative side, pass up those articles for me. I'll separate. You keep the that's yours. You're not feeling creative? You're an artiste. Alright, so if I were to say I had 50 milliliters of benzene, 60 milliliters of ethanol, and I was making a solution out of both of those. So 50 mils of benzene, 60 mils of ethanol. Who is my solute? The benzene, why? There's less of it. Yes, you always have less of your solute. You always have more of your solvent. Okay? The job of these are separate at first, and then they come together in a solution, right? So I'm going to show you my complex picture. Because you need to know this process anyway, so I might as well show you it in a picture form because it's way cooler than me telling you. So in this case, there's a step-by-step process that has to occur for a solution to form. You might want to write down a little bit of these details in my picture or your picture. I don't really care. So the solute in this case would be like sodium chloride. You have to break this apart into sodium plus and chlorine minus for it to dissolve, right? Do you think it's going to be hard for me to break that sodium chloride apart, or easy? But did we just talk about lattice energy earlier? Did we say ionic bonds are the strongest of all bonds? Okay, so there's a high amount of lattice energy here. So now what do you think? Hard. It's going to be hard to break apart. So do you think I'm going to put energy into breaking those bonds, or is it just going to happen by itself? I'm putting energy into it. Is that endothermic or exothermic? Endothermic. So is delta H positive or negative? Endo positive, right. It's added to it. So that's an endothermic process. Just simply saying, hey, solute, let's pull apart. All right, then there's a second step. So that's what I'm showing you. I go from step 1, where it's just particulates together, to the rest of step 1, which is its separated part, so it says expanded solute. The solvent has to do the same thing. So the solvent usually doesn't look this crunched up together, but it is somewhat together. So, like for example, water likes to stack with water in the hydrogen bonded form. If I want to take water 1 and water 2, and they're like hydrogen bonding, they're like, right here next to each other, do you think it's going to take energy for me to pull them apart? Or it's going to release energy to pull them apart? Well, see how I'm doing work, I'm like, hey, let's break that hydrogen bond. I have to overcome that hydrogen bond, right? So I literally have to break that attraction. That's not easy either. So that's actually me putting in energy again. I have to put energy into that hydrogen bond breaking. I'm going to say breaking because it's not really breaking. But I have to put energy into that process. So that is also another delta H that is positive, endothermic. Okay? Last one. Whenever I have sodium chloride that are broken into the ions, and I have water floating around, these guys, they want to interact with each other. They do, because the sodium plus has a plus on it. What part of water wants to be with sodium plus? The hydrogens or the oxygens? Why the oxygens? Yes, because the oxygens have those little lone pairs on them, right? Same thing over here. They have those little lone pairs on them. So they want to be together. And then also chlorine's the same way, but chlorine's got the negative charge, so who's attracted here? Hydrogens. So the hydrogens and the O's over here. The hydrogens, O's over here. All right, so these like each other. They want to be together. That's an energy lowering process. Energy lowering process. So if it's energy lowering, is it taking energy in or releasing energy? Releasing. So say delta H is what? Negative, right. Delta H is exothermic. Okay, so there's a process here though. You have to add step 1 to step 2. Those are both endothermic, right? So if both of those are endothermic, H1 plus H2 is endo. H3, which is the last step, step 3, is exo. If H1 and H2 are more endothermic than exothermic, the whole process overall is what? Endothermic. Will that feel cold to the touch or hot to the touch? Cold. Okay, less warm. Thanks. Less kinetic energy. So if that's greater than that, then it's cool to the touch. If this whole endothermic process is actually less endothermic, then this is exothermic. This will feel what? Hot to the touch. So a lot of things we are going to talk about, you're going to feel heat released or you're going to feel heat taken away from your hand. So I want you to know why. It's because the solution process, this is overall called the solution process. It's because of the energy it takes to break the bonds and break the solvent apart and the energy that's released when they're put together. It's not easy as like just pouring something in water. It takes a lot of stuff. Okay? That's a process. I'll let you observe that for a minute if you need to. You want to take a picture of that? I don't know if it's actually all the way on. There you go. And all this, of course, I'm videoing right now too, so it'll be online. All right, next step. Let's do the solubility curves that you guys have on your desk. Oh, I just talked about this. What dissolves like? Know that rule. Salt dissolves in water because salt, sodium chloride, will have same attractions or similar IMFs. So ions attract to hydrogen bonds, or the waters through hydrogen bonding. Oil and water don't mix because what? Oil is nonpolar. So if oil is nonpolar, it's not going to hang out with water because water is what? Polar. So you know that oil and grease, and if you ever have had like some waxy stuff in your hands, it does not wash off very well with just straight water. What does it wash off well with? Soap, because soap is being wet. Remember my soap molecule I drew? It holds hands with both sides, right? It holds the waxy side and the water side, and it brings them together. All right, tell me if we know the word immiscible. That was in your reading guides exchange. Immiscible? Right, they're insoluble in one another. They don't mix. So immiscible means don't mix. Miscible means it does mix. So today's kind of fast, but a lot of this stuff is fairly, like, almost common knowledge because you guys are smart people and you've experienced life. You know stuff happens like this, so it's not new. Oil, though, oil and grease will dissolve in gas. What's gasoline made of? You know the numbers on there, like 93, 97. What is it? Octane numbers, right? Well, what's octane?
C.
8. 18, thank you. That's 2n plus 2, octane. So gasoline is just octane. Well, that's nonpolar, and guess what? Oil's nonpolar, so they can dissolve in one another. Okay, so that's a good thing. So we need some things to dissolve gasoline or oil occasionally. All right, I think I just briefly talked about that. Okay, so I want you to tell me why some things dissolve and how or why it does it. Okay, so factors that affect dissolving ability or the solubility. So a lot of times when we use the word dissolving, we're talking about solubility, which is how much it dissolves or how fast it dissolves. So if you're at home and you're making sweet tea or Kool-Aid or whatever, what do? You do what? You stir it. Okay, so that's one thing. What else? You heat up the heat up the water, the salt. Okay, what else? So that's the agitation, that's the stir, right? What if you just keep on adding sugar? Is it just going to keep on dissolving? Why? What's it mean? It will be what? It'll be super saturated. It will reach its saturation point. Like, I can only have so much sugar in tea, right? I mean, I would love to have more sugar in tea, trust me. That's why we put like Splenda and stuff in there, because it's not sugar. It's going to dissolve itself too. Anything else you can do to make more stuff dissolve? Pressure is a different story, but yeah, we're going to get to that. So you guys know most of this, okay? You know. Oh, I didn't. Hold on. Okay. Who's ever had like a salt lick for a deer or a big sugar cube? You've seen these big salt blocks, right? Deer like that, so they have like surface, area to come lick. But if you were trying to dissolve a certain amount, would you choose to dissolve a big block of sugar or salt, or like lots of tiny crystals of sugar or salt? Why?
Because it's more
Okay, it's easier to dissolve because there's more surface area, because they're separated. There's actually more surface area on all those little crystals added together than that big, huge salt block. So that's additive after you've added them together. So the things that make, can I just delete this? The things that can affect dissolving ability or solubility are, if they are going to dissolve, like is it polar and polar, or is it nonpolar and nonpolar? If not, they don't want to dissolve with one another. So that's called the nature of the solvent and solute. The second thing is stirring something or agitation. Now that doesn't say if I stir to infinity and beyond, it's going to keep on dissolving. It's going to stop at the what point? Yeah, stop at saturation point. not amount. It'll change the rate of dissolving, but then not the amount that dissolves. Okay? So it's going to stop at saturation. Temperature, we talked about heating it up. It will dissolve more if you heat it up most of the time. Like sugar will dissolve more amount if you heat it up, but eventually it's going to also stop at the saturation point as well. And then surface area, like we just said, a big block is less soluble than all the particles because of the surface area that these have that doesn't have. Yeah.
So if you heat up something, you can like add like more dissolving on whatever.
You can add more up to a point though.
It cools down, like it doesn't somehow crystal come back down.
Yes, that's called desaturate.
Oh, it can do that?
Yeah. If you, so I'm going to show you something in a second actually with that. But if you heat it up to an extreme temperature, more of it will dissolve, right? But then let it cool back down, all that stuff's going to stay dissolved. It will, unless you disturb it. And it's like, oh crap, gotta go back to crystal form because it just can't hold that nice picture anymore where it's all dispersed equally throughout the solution.
How do you disturb it?
Oh, let me see. Let me see if I can show you. All right, so this is a very finicky solution. I'm gonna have to carefully bring it to you. Stirred. Okay. No, I'm not like that. Something like that. I've been exposed. No! Oh gosh, hold on! Right here! It's just right here itself. I just talked too loud and vibrated the solution and it did it. Did you see the liquid solution over there? And now it's a rock. I can't super saturated. Like it literally.
That's sarcasm?
No, I'm serious. I'm talking too loud. And it all of a sudden dissolved out or it desaturated. And it's formed. Pass around. Want to run a super saturated solution. I didn't get a chance to show you. So you saw the liquid. Yeah. It'll come into contact with each other and they'll go, oh man, we must be going to solid form. And they all do. So it's warm. You can pass it around. Yeah, just looking through it. So the what? Because the frequency of my voice and the loudness of my voice causes the particles to also vibrate at a higher frequency. When the particles vibrate and they touch another particle, and then they start to coagulate together, which means they come together and then they start to turn to solids. No, that's sodium acetate. It's actually somewhat expensive. That's why I like that bottle. Just that's probably like $50 or $60. Plus the flask is probably like $70. Because I have to put so much sodium acetate in there because it's super saturated. So it's holding more than it should right now.
You can turn water, right?
It's kind of wasn't water. It was a solution of sodium acetate. Yeah, I can turn that back. It just is a process.
Okay.
So pass it on.
$50.
No, I can definitely turn that back. No, but I keep those forever because if I have to use more of it, they're gonna kill me for using all the money. So I'm gonna explain more super saturated, but Kevin wanted to know, so I just went ahead and showed, but then went too fast and I'm real loud. So that's okay. Okay. But I'll tell you a little bit about right now. So the vibrations of my voice can cause particles, like the air around me right now is vibrating at the same frequency of my vocal cords. So you know your vocal cords are literally cords. They're like strings. They're literally like 3 strings or more. And you're pushing breath through your lungs. The lungs push the air through here. And it's like I don't want to say guitar, but it's like something waving the wind. It starts to go like this, right? One second. So as it goes through the strings, it causes your strings to vibrate at some sort of frequency. And that gives your voice the pitch that it has. So people who have, and that's actually so big fat cords, they don't vibrate very well, so that leaves you with a lower voice, deeper voice. But if you have really thin cords, with most females genetically attain, it'll have a smaller frequency, which is a higher pitch. Yeah.
So is it have you ever had a gum burster or something, and you blew at it, you made a whistle sound? Is it kind of like that?
Yes, it's exactly the same thing. So the frequency of my voice carried through the air particles touch the water, the particles that are touching the water, transferred it to the solutes, the solutes desaturated. Okay, so let's talk about saturation and solubility. If you want to write down this bit right here, you go for it. The main thing I need you to know is that at every temperature and pressure, there's a specific solubility. And the solubility is not in willy-nilly units. They have specific units that are grams of solute per grams of solvent, which is water. Huh?
At every temperature and pressure, there's
A specific saturation point. So the amount of solute that dissolves in a given amount of solvent is specific to a temperature and pressure. So, like for example, our sweet tea example, sweet tea, you can have, I don't know, 10 grams of sugar per 100 grams of water at 25 degrees C. But if you increase the temperature, it's going to be higher. So increased temperature, let's go to 50 degrees C, it'll be at maybe 20 grams per 100. So it's very temperature dependent.
What about
Pressure, so this is assuming one atmosphere, but if pressure changes, solubility changes. I'll show you the graph in a second. I'll show you the graph in a second, okay? All right, back with me too. Keep passing, but back with me. I don't know if it stayed warm any longer. Is it still warm? A little bit? Okay. So this saturated solution is the specific number that I'm looking for. So saturated at 25 would be 10 grams of sugar per 100 grams of water. Every salt, so ionic compound, is a different solubility. All right, so what does it mean to be saturated? This is literally what it means to be saturated. I'll show you the gases in a second. I will go ahead and note that it's per liter this time, not per 100 grams of solvent. So gases are different. We talked about the whole dynamic equilibrium. So that word is also used today in saturated solutions between solutes and solvents. So the way we can write it out, so you can see this, can you guys see this picture down here? You can see the water attacking the solute. So the way this looks when you write it in a chemical equation is sodium chloride solid equilibrates. So it's a reversible arrow, so it can go back and forth and back and forth and back and forth between that solid and sodium chloride in its aqueous form. That's what dynamic equilibrium means. Equilibrium shows the double-headed arrow. Yeah.
Is that theoretically we make T cubes?
T cubes, it would be sucrose mainly with T particles within it. It would be mainly sucrose. So T has a different solubility breaking point. I can look it up. Okay, but it's easier just to freeze it. And so you can see that this dynamic equilibrium, what's the word dynamic mean? Constantly changing, right? So this whole, I'm going to dissolve and then come back together, dissolve and come back together, dissolve and come back together. This is a cycle. It'll continually be changing all the time. That's why it's called dynamic. All right, we're going to the graph. In this graph, oh yes, this is on your paper, yes? This graph?
Yes.
Okay, if you want to write this on your paper, that's fine. If you want to jot it down elsewhere, that's fine. That's your paper. So the definitions of saturated, supersaturated, unsaturated are pretty well saturated, it's full. Unsaturated, it's not full. Supersaturated, it's over full and unstable. I heat it up to a high temperature, so I put more stuff in it than should be in it. I heat it up really hot, and then I don't touch it. I let it cool back down to temperature without talking around it, breathing around it, touching it, don't disturb it. It's very unstable.
How hot is it?
I just heat it up in the microwave. So hotter than it should be. But it's still like, it was boiling, so it was like over 100 degrees Celsius.
How long is the microwave?
2 minutes.
I can get it from the microwave there.
I walked like a ninja. Yeah. So saturated means the maximum amount for a given temperature, it's full. Unsaturated, it does not have maximum amount, so it's not full. Unfull is not a word. All I can think about is that Taco Bell commercial. I'm full. Okay, and supersaturated solution, it's over full. And all these are at a specific temperature and specific pressure. One note to make is someplace around your graph, say the line represents, which of these do you think that line represents?
Okay, which line?
So like for example, this line right here for sodium nitrate. Do you think this is the line of saturation, unsaturation, or supersaturation? Saturation. So the line represents the saturation. So for example, I'll show you to read this graph now. At 50 degrees C, how much sodium nitrate can dissolve in 100 grams of water? Look at your graph too. So all you're doing is reading a graph, right? You're going to say at 50 degrees C, 50, you look up until you see sodium nitrate. At sodium nitrate, you drop the line to the left to look at the area on the y-axis that describes the solubility. You'd say maybe like 115-ish, plus or minus 5. So that's about 115 grams per 100 grams of water. That's how you read a graph. All right, what do you notice? Well, no, we'll do the notice thing in a second. You need a break real fast? You need a break? Okay. Yeah, you need a break. Take a 30-second break for yourself, and I will show you my video, which I think I've shown you part of it already. Okay, and be good movie watchers. Let's get this.
In the usual way, the molecules of water take the atoms apart. A salt solution form, but that's only the start. Homogeneous state crop. Homogeneous state crop. Solids that are polar dissolve solids that are polar or ionic. That is really cute. Water and unpolar science just won't mix, but a non-polar solvent like an can mix. Like dissolves life, polar and polar. Like dissolves life, non-polar and polar. And all the solid molecules use couplers. The solid ion in your cup. Solution saturated in its full or short. Solubility's been reached by that paper of jar. Saturation on the line. Saturation on the line. Still some water molecules unstuck. We're still in the salt. Polar in rock. Solution is unsaturated T2C. You haven't yet reached the science we have to see. Unsaturated. Unsaturated. If you go more solubility than can be dissolved, then there's saturated situations involved. The dissolves that is a precipitate. What the solution is stable, so you ascertain. Supersaturation. Supersaturation. The solvents of the water in a vapor today. It has to part in the usual way.
Oh, okay. We'll watch the rest of this when we do collective properties. Yay. And back. I think that's all we have to do here. Okay, let's read the solubility graph. Look at mine first, and then I think, what did I write on yours? What's the first question for you?
For which solid solubility least more affected by.
Alright, do you guys have these questions? Down below that graph? Okay, answer these questions with me. How many, okay, so the line represents what again? Saturation. How many grams of, what's the name of this? Potassium bromide will dissolve in 100 mils of water at 80 degrees C. So look at my graph. You might be able to see it on your graph too, but you can see this potassium bromide line right here, right? Cool. 80 degrees C. How much about can you read from here? 100. So you're looking up at 80. You see, I'm sorry, that line's a little higher. My drawing skills are horrible. You say 100, right? So then the answer is how many grams? Well, 100 grams of potassium, potassium bromide will dissolve. What if instead of me saying 100 grams, 100 milliliters, I put 200 milliliters here? How much should be able to dissolve in 200 milliliters? 200 grams. You just double the amount, right? There you go. All right. How many grams of, what's the name of that? Nitrate will dissolve in 500 milliliters of water at 10 degrees C. So what am I looking for? So let me look for sodium nitrate for you first, right here. Here's sodium nitrate. Here's 100. So that's 80 per what though?
80 grams.
That's 80 grams per 100 grams of water. So how much? Yeah. So times by 5. So, and this says milliliters. Well, how can I go from grams of water to milliliters of water?
Multiply by 1. What?
1. The density of 1. Thank you. Density is for water is 1 gram per milliliter. So you're literally saying for 500 milliliters, aka 500 grams, this divided by 80 divided by 100 times 100. I'll just show you them simple. It's just multiply by 5. So there's 5 times as much water. So what is that? 400 grams of sodium nitrate. All right, which salt is most soluble at 40 degrees? What do you do?
Yeah, and question the last one.
Yes.
Why are you dividing 80 by 100?
I'm showing you that it's 80 grams per 100 grams of water. So I'm not actually dividing. That's why I tried to cross it out. It's 80 grams per 100 grams of water, so it should be 5 times as much per 500 grams of water. All right, so what are you looking for here? So at 40, go up, 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 and sodium nitrate it is. Most soluble means most stuff dissolves per 100 grams of water. When 100 grams of KBr are dissolved in 100 mils of water at 60 degrees C, what type of solution is this? So this type of solution, you have 3 choices. What are the choices? Saturated, unsaturated, supersaturated. So 100 grams of KBr are dissolved at 60 degrees. So let's see how much should dissolve. Here's 60. Here's KBr right here. Go over. So that should dissolve, yeah, like 85 to 90, right? We put 100 in, so super saturated. What should happen if I disturb this? If I disturb that supersaturated solution? It'll touch crystals, it'll desaturate, it'll precipitate out. It does work. When 80 grams of sodium nitrate are dissolved at 10 degrees, what solution is formed? Sodium nitrate was my green line right here. At 10 degrees, yes, it saturates on the line. All right, you guys do the next one then.
Yeah, we have a different.
Yeah, so I'm sorry. For these 3 questions, use this curve. For these 3, use this curve.
ACL. Are you sure? I think it's ACL.
Yeah.
It's just, it looks like it's pointing at the same line, but it's not. It's correct. That's what I was saying. Essentially, that's what I said. I just don't.
I'm just listening for answers. Keep going. A lot of you guys are getting these right.
Oh, wait a minute. Just kidding. I didn't see this either. Oh, that's what I was saying. I don't think I spoke well.
All right, what did you guys say for the last one?
Temperature.
Increased solubility.
Indirect, right?
Cool. All right, so this is common sense day, right? And I think most of us are pretty aware of this stuff. You can see that the lines that are less changed are the horizontal lines, that's sodium chloride in this case. The relationship between solubility of salts and temperature are direct. Gases are indirect. Give me an example of gases being less soluble at high temperatures. Anybody? No examples. Give me real life. Give me something. Huh?
Wait.
So, give me an example of a gas being less soluble at high temperatures in real life. Huh? I think carbon dioxide's better because I think most people know what we're talking about here. So, but give me an example though. You said a word. Where would you find carbon dioxide in liquid solution? In soda. Carbonated beverages? Everything they're carbonated with.
Yeah.
Not carbon. Carbon's probably poisonous to you.
Oh.
Carbon dioxide. Carbon dioxide. Okay. No, okay, so generally, if I wanted to pop a soda, if it was sitting out in the hot sun or opening a bottle of cheer wine out in the hot sun, what does it do when I open it? So it's releasing all the gases. If I put it back in the fridge, well, if I put it back in the fridge, that's my goal. My goal is to try to keep some of the gases dissolved in it. Otherwise, they all pop out. Okay, so these are just general rules for you. Some of you guys are still talking. Forgive me. These are some general rules which you want to write down. I do recommend you writing down Henry's Law. That's the only thing that actually has a name to it. But generally, increasing temperature, gases get real excited. They remove themselves from solution by evaporating. Other than that, they stay in solution. So a cold beverage will be more bubbly and fizzy than a hot beverage, one that's been sitting out all day. So that's why if you pop a top to soda can, or you have a 2 liter or something, you want to put the cap back on because you want to keep the gases inside. 1 second. So gases are indirectly related because of that inverse relationship with the increasing temperature should decrease solubility. And that's because increasing temperature causes an increase in kinetic energy, and those gases with kinetic energy, they just leave. They just go out of solution. That's because they have the energy to do so. Pressure is different though. That's the one with Henry's Law. As you increase, okay, so in like a Coca-Cola, the museum down in Atlanta, who's ever been? Yay! Okay, so you've probably seen some of the processing if you were allowed to go and see that, where they force a bunch of carbon dioxide in the sodas before they close them up. They just pressurize those things like crazy. Why would they want to pressurize the little bit of air? So this is pressurized carbon dioxide, that little bit of air that's above the solution. What are they trying to do? They're trying to keep the carbon dioxide in the solution, right? Because people want fizzy drinks. They don't want juice. They buy juice, they don't want juice. They want carbonated beverages. So they're pressurizing it. So in this case, increasing pressure causes what to the solubility of the carbon dioxide? Increasing pressure on top of the beverage increases solubility. You'll notice that this is a direct relationship, just like our other gas laws. Anything that was on top of each other was direct. So as I increase pressure, I increase solubility. Increasing pressure, increasing solubility. So S1 over P1 is equal to S2 over P2 is called Henry's Law. And it's just basically saying this rule right here. That one right here. Increased pressure increases solubility if you're talking about gases in solution. Only for gases, yeah. Gases. Yes. Question? Okay. Common sense today for this stuff right here is just putting names and stuff to it there. I think I've got one more slide for you. Yeah. Well, I'll go to the next one second. Alright, this is one of the last things, and then I'll let you guys work on your process. You know the word dilute and concentrated means lots of stuff, not so much stuff, right? Like that's common sense. But when we use diluted and concentrated in chemistry, I just want you to know that you are going to be mainly talking about concentrations, right? So concentrated means concentrations. Concentrations for us, most of the time, is expressed as big M. You've seen big M a lot. What were the units for big M? Moles of solute over liters of solution. Liters of solution. And it's just, these are all, and so I better put aqueous concentrations that we're talking about. So we have to use these are like qualitative terms. I'm just going to say, yeah, a lot of stuff, not so much stuff. But when we talk about numbers, we're using molarity. That's why we always have a number in front of that M there. So 1 molar solutions equals 1 mole of sodium chloride over 1 liter of solution. What's the solution made of? 2 things. Okay, what's the solvent in an aqueous solution? Water. And what's the solute as for my example? NaCl. Yep. There you go. So this solution is made up of those two things. So we're going to start expressing things in their appropriate concentration units, which is molarity and then a couple of other things. Yeah.
What's the difference between molarity and
Molality, just the way it's expressed. Molality is moles of sodium chloride per 1 kilogram of solvent. Top number's the same, the bottom number's different.
Oh.
It's the same thing. All right, ready? We're gonna do one or two problems. We kind of go through this every time we do two problems, so I'm not gonna go through these steps. Knowns, figure out who your unknown is, and then figure out how to do the problem. That's always a 3-step process for this, so I'm not gonna go there. Alright, molarity is the one thing that we just talked about. It's moles of solute per liter of solution. Whenever you're saying something though, you say molal. You don't say molarity. So you'd say, not molal, molar. Sorry, we're talking about molality. Molality is the next one. So you'd say this is a 2 molar solution. When you see 2 big M sodium hydroxide, it's called 2 molar solution. I want to do this example with you. Okay? This is just concentration. So it's just a way of expressing, like, for Kool-Aid, I might put 2 packs of the fruit punch Kool-Aid mix in a liter of water. So it'd be 2 molar Kool-Aid, because I have 2 sections of that, 2 parts of that. So the molarity, though, in sodium hydroxide is just going to be 2 moles of sodium hydroxide. So in this example, what is the molarity? So question, what am I looking for? What's the variable for this? Big M, which is moles per liter, right? What's the molarity of a 5-liter solution containing 4.3 moles of sodium chloride? How do I set this up? Right, so these are knowns right here, and my unknown is that 4.3 moles, 3 moles of sodium chloride over 5 liters of solution. So that's like 0.8 something. 8.6, thank you. 6 molar sodium chloride. Thumbs up if you're cool with that. These math we've done in quite some time. That was the easy problem. Like, that's baby problem. Of course it's baby problem. I want to introduce the baby stuff. Yeah.
Is there a way to abbreviate solute solution?
I always do solution, S-O-L-N. Solute, I just actually name what I'm talking about. Like in this case, I'm talking about sodium chloride. Hold on, let me skip this. Molality is really similar, but what do you notice? Oh, I don't know if I fixed it. Did I fix it? Oh, no. This is solution. I'm sorry, not solution. Solvent. I've had the same typo for 3 years. Solvent. So that's the last one we're going to do today. Moles of solute per 1 kilogram of solvent. What do you notice that's different from molarity? Okay. But what's the first thing you notice? The little m. First thing I noticed is little m. The first one's a big M, the second one's a little m. I heard kilograms. What was the first one? Liters. So the first one was liters of what? Solution. This is solvent. So the denominator is entirely different. This is called molality. And when you say it, you don't go molality. You say this is a 2 molal solution. So 2 little m of sodium hydroxide is called 2 molal. Sounds like you've got some problem talking, but it's called molal. So question, what is the molality, question little m, of a solution that contains 55.4 grams of potassium nitrate and 300 grams of water? How would you like to try this? Okay, so you want to take this, go to kilograms? How many kilograms is this? Well, now, how do I know I'm using this as my solvent? Because water is a universal solvent and it's larger. Huh? Yes, solute. But this is also a large amount. Well, how many kilograms is this, people? 0.300 kilograms of water. All right, what do I need to do with this number? Change it to moles. So 55.4 grams of potassium nitrate to moles. What's the molar mass of that? Add it up in your head. 39.1 plus 14 is 43 plus 48. 91. Sure. Sounds great. Okay. 1 mole of potassium nitrate weighs 91 grams of potassium nitrate. Yeah. And you get to moles, which in this case is like 0.6. I'm making up numbers for simplicity's sake here. So 0.6 moles. What is it? Did you have it? What is it?
No, I think it was 101.
Oh, 91. 48 plus 40. I believe you. I thought it was kind of low, but I don't know what I did. Yeah, we'll go with that. Okay, so, and this, well, then this is a little bit less. What is it, 0.5? We'll go with 0.5. 0.5 moles of KNO3. So that many moles over that many kilograms is going to give us our answer. So all you're going to do is literally just plug it in 0.50 moles per 0.3 kilograms to give me 1.6. Thanks. Wow. If you have a certain number of moles, it's always written as per 1 kilogram whenever you are literally like talking about it. If I give you 2 mole solution, you're going to assume that's 2 moles per 1 kilogram. So that's if you start with a number like this. If you're calculating you're calculating it yourself, you put numbers you specifically got, and then this is understood to be 1.6 moles per 1 kilogram if you were to like do it per 1 kilogram. But this is literally how much we had, so we had to use that. All right, so on your problem set, you guys have different types of problems, but I want you to only do the ones that are related to molarity and molality for now. So looking at numbers, concentration lecture problems, go through the ones that you can do based on the 2 partner. We don't have as much time left as I thought we did. We are now ahead though. You have, you'll pass it up in a second. You have 15 minutes. I'm sorry, the lecture. You're in the lecture. Can we do it on the back of our notes, or should we not? Yes, you know back of your notes. All right, I'm going to answer those questions one more time, just so you can hear me. You have 15 minutes. You can probably get through all the problems that relate to molarity and molality, actually. You just have to filter through them, because I'm not teaching all the concentration facts. We'll do the rest of this tomorrow. Okay? When you're done looking at the set or reading about 15, 16, if there's any last little things that you need to look at, you took notes on it, pass those up. And you guys don't have much for homework. You need to continue. Concept 15, 16. You won't be able to finish the lecture problems, so you can't finish those today. You can only do the molarity and molality ones.
What is it?
Yeah. It's 15, 16 combination.
Oh, okay. When does our due date out?
Yes. Yeah, I can tell you.